Section 5.2, exponential functions. Okay, so this section focus on, of course, exponential functions, but we're going to really talk more about how to predict the way the graph looks. Okay, there's no good way to graph these directly without making complicated tables, but even then they get kind of complicated. So, and as I said, complicated tables. And so it's good to be able to kind of predict what they're going to look like. It helps to understand what the transformation of functions, if you think back to chapter 2, when we talk about transformation of functions, keep that in mind, because that really does help. Okay, so let's just start off by writing out our first example here. I want to sketch the graph of f of x equals 5 to the x power. Okay, and it's kind of helpful to, at least for this one, think about the table, right? Think about what a table would look like here. Okay, and maybe not draw out the table, but let's talk about it. If you plugged in 0, you would get 5 to the 0. I remind you that that always equals 1. Anything to the 0 power will always be 1. So it's not uncommon for your exponential function to have the point, the y-intercept 0, 1. Okay, that's our normal starting point. Okay, now think about it. When x is 1, y would have to be 5. Right, because 5 to the first power is going to be 5. Okay, when x is 2, that's 5 squared. Think about that. We just went from 1 to 5 to 25. That would be actually off this page. Okay, so we know this side of the graph does this. It skyrockets up. Okay, well, think about if you started putting in negative numbers, right? What's 5 to the negative 1 power? Well, remember, a negative exponent just means flip it over, right? So this is 1 over 5, okay, a fifth. 5 to the negative second power is 1 over 5 squared, which is 1 over 25. I can't even get it closer than that. 5 to the negative third power is 1 over 5 to the third, which is 1 over 125. Okay, so at that point it's basically 0. But it never actually equals 0, right? No matter what, you can't make that exponent force the number to equal 0. So the x-axis becomes a horizontal asymptote, and the graph starts to hug it. Okay, so this is the general graph. Right? So this is kind of an ugly one, but, oh, okay, that was worse. You know what? I'm just going to off to the side here and say this is what the general graph looks like. There we go. That one's better. Okay, that's your regular function, f of x equals some number raised to the power x. Okay, so that's the general one. Now let's imagine I want to graph a variation of that. Let's say I want to graph f of x equals 3 to the negative x. 3 to the negative x. Okay, so you may remember from transformation of functions, when you change your x to a negative, you're actually reflecting the graph across the y-axis, right? You're flipping it horizontally. Okay, so let's see, what would this graph look like? We have some important points here. I cannot draw a straight line today. We know it crosses at 0, 1. Okay, unless we started adding stuff outside of this, right? But if you plug in 0, you get 3 to the 0, which is 1. Okay, so instead of doing this, I want to reflect it. So I actually want it to go the opposite direction. It's going to go up this way and then hug the x-axis going that way. So looks something like that. That might be the best one I've ever drawn in my life. Right there, congratulations. Okay, notice whenever x is negative 1, it's going to cross at 3. And I messed it up. Let me not mess it up. We'll just say it crosses at 3. At negative 2, it would be at 9. And then at negative 3, it'd be at 27. And then, it's way up too high. Okay, so understanding the transformation of functions really helps you to predict what that graph's going to look like. Okay, let's do one more of these. Third example here. let's graph 3 minus 3 to the x. Okay, so 3 to the x, we just talked about what that one looks like, right? That one looks, crosses at 1, at 1 it's 3, so it does something like this, something like that. Okay, that would just be this. If there is a negative situated outside of that 3 to the x, remember a negative on the outside means to reflect it across the x-axis. In other words, flip it downward. So instead of being up here, it's going to be down here, right? Reflect it. Okay, so I'm going to go ahead and draw it down there then. Those points should still be the same in a certain sense, right? This should be -1, and this should be, and I know this is not drawn well, -3. Okay, so that takes care of the negative in front of the 3 to the x, but there's also this +3 that's tacked on. Remember, a positive value tacked on raises the graph up. It shifts it up. Okay, so I'm going to shift this graph upward. I want to make note of the fact that this is the horizontal asymptote, because I have to shift that up 3 spaces as well. So if I shift that up, that would be at 1, 2, 3. This point here, shifted up 3 spaces, would be 1, 2, 3. Now it's crossing at 2. This point right here would be shifted up 1, 2, 3. That's at 0 now. All right, so this graph is now here. All right, not my greatest graph, but I think you can get the general idea. Let me kind of redraw it to clean it up. The horizontal asymptote, right? This was the x-axis, right? Is here. It crosses at 0, 2, and then it crosses the x-axis at 1, 0. There we go. So the graph would look something like that. Okay. Not too bad, right? Okay. Again, the trick is to pay attention to what the graph of the exponential part would be, and then do all the transformations around it. All right. Because we were talking about exponentials, right? I should also, of course, mention the most famous exponential function out there, and that would be the function e to the x. Okay, so I need to briefly describe what e is. You think about pi, right? Pi is a irrational constant, 3.14159, blah, 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 right? It goes on forever. Okay. E is just like that, except it's more of a naturally occurring number. If you ever take differential equations, right, which is a class you would take after you take your calculus courses, you'll see how fancy E actually is, right? But E is approximately equal to 2.71828 something, 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 right? And it goes on forever, just like pi, okay? Pi is a really interesting number. Anyway, and so it is a number, so that's how you have to think about it now. Don't think about it as a letter, think about it as a number. And so, for example, if I asked you to find e to the 10th power, you could just type that in a calculator, right? I wouldn't expect you to be able to do that by hand. And that comes out to be 22,026.46579. I'm rounded off to 4 decimal places. Okay, so don't be surprised if you see problems like that. It's just basically to make sure you know how to type that in your calculator, right? And you just push the E button. Sometimes it has a little caret symbol. Sometimes it's a little blank. Sometimes it says e to the x, and then you type something in. Anyway, find that E button. It's a good button. All right, finally, the last thing I want to talk about when talking about exponential functions is one of the applications of it. Okay, this is a practical application, and it deals with compound interest. Compound interest. And so there's a formula. A equals P, A like amount equals P principal times 1 plus R, the rate as a decimal, over N, how many times a year it's going to be compounded, raised to the N times T, number of years, power. Okay, and so again, N, how many times per year it's going to be compounded. So if it's something that's compounded monthly, right, like if it's a credit card and it accrues interest each month, okay, that would be 12, right? And it would be 12 because there's 12 months in a year. If it's annually, it'd be 1. Semi-annually would be 2. Quarterly would be 4. Okay? All right, so anyway, weekly would be what, 52? All right, anyway, so let's do an example. Let's find, I think we're on example 5 now. Let's use this formula to find an account balance that has with the given conditions. Okay, so I'm looking for an account balance where initially deposited was $12,500. The rate, the interest rate, was 3%. It's compounded quarterly. And the time was the account balance going to be after 3 years. Okay, so there's a typical problem here. And I'm just going to use the formula. What is the account balance when I put $12,500 into this account? The rate has to be written as a decimal. So instead of 3%, you would put in 0.03. If it's being compounded quarterly, that means that N is 4. Raised to the N is 4. T is 3 power, so it's going to be 12th power up top. Okay, I'm going to just type that in the calculator. All right, that's all I'm going to do. All right, so if I type this in the calculator, I get $13,672.59. It's a pretty good return, unless of course you're talking about debt, in which case not a good thing. Okay, so anyway, that's how you'd use that formula. And so that's about as much detail as we'll go into with exponential functions. You'll see that we need to learn a little bit about logarithmic functions before we can really start having some fun. So that would be section 5.2, exponential functions.